Hello, I'm going to present this paper, Solar Energy Forecasting with Fuzz Time Series using high order fuzzy cognitive maps. This work was developed by the PhD student Omi Doran, the first author, in collaboration with Dr. Rodrigo Silva from the Federal University of Ouro Preto, Petrônio Silva from the Federal Institute of Northern Minas Gerais, and I am the advisor, Frederico Guimarães, from the Machine Intelligence and Data Science Lab, the Federal University of Minas Gerais. This is the summary of this presentation. Skip this. Time series forecasting is a very active and challenging field with many applications in economics, medicine, energy, and management. In 1993, Song and Shinson introduced the concept of fuzzy time series. It's a method to fuzzify time series data and extract fuzzy-based rules for forecasting. This method has the advantages of generating a model that's explainable, flexible, and readable, in contrast to some traditional methods, including other machine learning methods. Since then, there are many methods, fuzzy time series methods that have been proposed in the literature, but all of them basically include the stages of defining a universe of discourse and fuzzy sets in this universe of discourse. Then we have to perform a partitioning of this universe of discourse. We fuzzify the data points into a sequence of fuzzy sets, then generating a fuzzy time series. From this historical data and the fuzzified time series, we generate a fuzzy rules. And the fuzzifying these fuzzy rules, we obtain a forecast of the model. It's well known that the accuracy of these models, the FTS models, is significantly affected by the use of weighted rules or not. And fuzzy cognitive map is a kind of weighted method that was adopted by Cosco according to the cognitive map theory. So given this context, the research goals of this paper is to use fuzzy cognitive maps to generate the rules in the knowledge base of FTS method. So the idea is to combine the learning capability of FCM to model the time series data automatically and discover not only the rules, but also the weights of these rules. So the main contribution of this paper is adopting a hybrid method for time series prediction, in which the weight matrix associated with each fuzzy rule is learned by using genetic algorithm. So a fuzzy cognitive map is defined by 4 elements. We have a set of n concepts, the vector C with the concepts, a matrix W representing the weights relating these concepts. A is a vector of activations for each concept. It represents the state vector of these concept activations. And F is an activation function or transfer function used to generate the state vectors. So in fuzzy cognitive maps, the weights are used to perform the transition from the current state to the next. So as in equation 2, the next state vector, A of t plus 1, is given by the activation function of the weight matrix times the current state vector. A high order fuzzy cognitive map modifies the original model by including legs of not only the current state vector, but legs of the previous current vectors. So in this work, we propose a new hybrid forecasting method combining high-order fuzzy cognitive maps with fuzzy time series. The architecture of the model is represented in this figure. We have here the universe of the discourse, the range of the time series. It's partitioned into a set of concepts. Each concept is associated with a fuzzy set. From the historical data, we obtain a weight matrix relating the concepts. And this weight matrix and the concepts can be represented in the form of a graph, a directed graph, which is the fuzzy cognitive map. Here's how the fuzzy cognitive map is combined with FTS in our method. So we have a time series, we have the partition of the universe of discourse into some concepts. The sample in time t-1. From this sample, we obtain the activations of the concepts, which is a state vector f of t-1. From the sample y of t, we obtain also an activation of the concepts ft. And then we obtain the next state vector here from the weight matrix in leg t-1 times the state vector in t-1 plus the weight matrix wt times ft. From the next state vector, we defuzzify and obtain a forecast value. This diagram shows more detail of the proposed method. We have first the training process. The training process consists of defining the universe of discourse and partitioning. We used grid partitioning method and triangular membership functions. We tested 5, 10, and 20 concepts, different concepts. The matrix, the weight matrix learning process is done by genetic algorithm. And after obtaining these weight matrices, we can use the model for forecasting. In forecasting, once we have a sample, we fuzzify the sample, obtaining the state vector, which is given by the membership values of each concept. We calculate the activation of the next state vector by applying the transition rule of FCM. And then we apply the defuzzification, which is given by the weighted sum of the midpoints of each concept, weighted by the activation of each concept. And then we have an estimation of the forecast value in t+1. In the computational experiments, we use public data of solar energy forecasting. In this experiment, we have 8,000 samples using a sliding window of 2,000 samples. 8% of the window for each experiment, right? 8% of the window is used for training the model and 20% for testing the model. So the errors reported here are based on the test data. Here are the results of our experiments. First, we tested the use of the bias term in the model. So comparing the HFCM-FTS without bias and with bias, the performance with bias is significantly better. So it's recommended to use the bias. In this experiment, we evaluated the influence of the activation function. We test 3 different activation functions: ReLU, rectified linear unit, sigmoid, and tangent hyperbolic. Although the ReLU had better results, it's not that significant, the difference with sigmoid and tangent hyperbolic. So it doesn't seem to be very sensitive to the choice of the activation function. And finally, the last experiment, we perform a comparison with other fuzzy time series methods. In particularly, we compare our model with high order FTS, which is a model that does not use weights. The weighted high order FTS, which use weights for the learning for the fuzzy rules, and probabilistic weighted fuzzy time series, which is a novel method with a very high accuracy. So comparing here the average values obtained by our model for 5 concepts, we achieved much better results than the high order fuzzy time series, showing that the use of weights really improved the model. It's also better than the weighted high order fuzzy time series, showing that the way the weights are used in FCM produced much better results than the weighted high order fuzzy FTS. And it's also better than PWFTS. For 10 and 20 concepts, the performance of the HFCM-FTS model is degraded, but we conjecture that this degrading performance is due to the increase in the number of parameters and maybe non-convergence of the genetic algorithm for learning the parameters. So the conclusions, the core contribution of this paper is the design of hybrid method using fuzzy cognitive maps. We use genetic algorithm as a learning method to find the weight matrix, and the proposed method presented competitive results when compared to other fuzzy time series methods in the literature, especially when the number of concepts is limited. Despite the success of the presented method when the number of concepts is low, the proposed training methodology is very time-consuming as the number of concepts increases. This issue is more important when we use this model for multivariate fuzzy FTS. So this is part of the future research. We want to implement a multivariate version and a probabilistic version of the method. Thank you very much.